Hello, my name is Revan Joshi from Ashburn, Virginia, and I'm a senior in high school. For my research project, I developed a way to propulsively land solid fuel rockets. Over the next decade, thousands of satellites will be deployed into orbit, and humanity will enter a new stage in space exploration. The main problem standing in the way of this future is the cost associated with rocket launches. Space companies have started propulsively landing their rockets with the intention of future reuse, but this still leaves many problems unsolved as the liquid rocket engines used require extensive refurbishment between launches, leading to large turnaround times. The alternative solution would be to use solid fuel rocket boosters as they are cheaper, more energy dense, and easier to refurbish. However, solid fuel rockets have their fuel and oxidizer premixed and therefore cannot be throttled, which would make propulsively landing them impossible until now. In this project, I developed a way to artificially throttle solid fuel rockets by vectoring the thrust away from the ground. Nearly every rocket produced today has an engine gimbal that allows for thrust to be vectored. This vectoring is what controls the rocket's orientation as it travels through the air. When thrust is vectored by a significant amount, the vertical component of thrust decreases, providing an effect similar to throttle control without actually altering the thrust output. This, however, creates a horizontal thrust component which will cause the rocket to rotate about its center of mass. So to counteract this, the thrust is diverted in a circular pattern with the divert radius changing as the rocket approaches the ground. To organize the methods for this project, I divided up all the procedures into three main objectives. The first objective was to create a simulation that tested the feasibility of propulsive landing on the model scale using solid fuel. I used the 3JS JavaScript library to model the simulation as it would allow for the use of vectors and quaternions to accurately simulate rotation and translation in 3 dimensions. 3JS also allows the simulated rocket flight to be animated in real time. The simulation I created shows that propulsively landing this rocket safely is possible when the rocket motor is ignited 6.5 seconds after launch. This, however, does not account for air resistance, turbulence, wind, gimbal misalignment, or ignition delay. After programming these variables into the simulation and randomizing them before each launch, the rocket is no longer stable and fails to maintain a vertical trajectory, much less propulsively land itself. The second objective was to manufacture physical control systems that change the orientation of the rocket. To perform the artificial throttle control maneuver, a thrust vector gimbal was needed to divert thrust away from the ground. The gimbal was designed in Autodesk Inventor and 3D printed from PETG plastic. The choice to use PETG over the more traditional polylactic acid was made due to its higher glass transition temperature, which is able to withstand the heat from a model rocket motor casing. Two high-accuracy digital servos were used to control the two axes of the gimbal. The control system is able to create torques that rotate the rocket around its x and z axes by vectoring the thrust. To control the roll axis, a reaction wheel was constructed and placed near the center of mass in the rocket airframe. Aluminum was used for the construction of the wheel as it has a high mass moment of inertia, providing greater control. A 12-volt brushed DC motor was used to spin the reaction wheel, as unlike the brushless variety, brushed motors have a less aggressive stop when polarity is reversed. Reaction wheels work by utilizing the law of conservation of angular momentum. When the reaction wheel is spun, the rocket also spins proportionally in the direction of rotation. Both these control systems connect to a custom flight computer that runs all the flight software on board the rocket. It houses a gyroscope, accelerometer, magnetometer, and altimeter, which all provide orientation and motion data to be used in the next objective. The flight computer is also able to directly interface with the simulation and actuate the control systems in real time as the simulation is running. The third and final objective was to develop two PID controllers that would stabilize the trajectory of the rocket and control the artificial throttle maneuver. Since the rocket has no fins to provide passive stability, the thrust vector gimbal was used to create torques that actively control the orientation of the rocket. The thrust vector control algorithm works by measuring the rocket's angle, angular velocity, and angular absolute. These three values are multiplied by randomized coefficients and inputted into the PID equation, resulting in a control system actuation command. Initially, the randomized coefficients performed poorly, but with the help of a genetic algorithm I wrote, these coefficients were significantly optimized. The artificial throttle controller is what allows the rocket to bleed off excess thrust from the solid fuel booster. First, the flight computer intentionally ignites the landing motor early to ensure that the rocket will burn out before touching the ground. The controller then measures where the rocket should be against where it currently is. If the rocket is too low, the gimbal remains upright. If the rocket is too high, thrust is artificially reduced by diverting it away from the ground. The following four simulations show individual tests using different combinations of the controllers. In the first simulation, the rocket is very unstable and proceeds to crash due to a lack of control. In the second simulation, the thrust vector controller is able to stabilize the rocket. However, since there's no artificial throttle control, the rocket crashes into the ground during landing and proceeds to take off again due to the excess thrust. In the third simulation, the thrust vector controller is disabled and ascent turbulence is removed to allow the rocket to reach apogee. During the landing phase, the artificial throttle controller attempts to divert thrust, but the rocket quickly spirals out of control as there is no thrust vector controller. In the final simulation, both the thrust vector controller and artificial throttle controller are enabled. This shows how both controllers are dependent on each other and together allow the rocket to land safely. To test the reliability of this novel approach, 1,000 simulations were conducted. The rocket was able to safely land in 974 of the simulations, providing us with a landing success rate of 97.4%. Out of the 26 failed attempts, 17 were caused by hard impacts due to insufficient throttle control, 5 were caused by the rocket toppling over due to a tilted orientation at touchdown, 3 were caused by multiple factors that individually would have not caused a failure, and lastly, only one simulated landing attempt was caused by instability in flight, which shows that the thrust vector controller is working exceptionally well. The results from this project so far show that the novel approach to artificial throttle control on solid fuel rockets is able to perform a propulsive landing with a success rate comparable to the liquid rocket engines used today. Extensions to this project include the construction and testing of a physical prototype rocket that will verify the results from the simulation. Thank you for watching my project video. I hope you enjoyed it.